Hello, Bazel Khan. I'm Sebastian. I'm an autonomy engineer at Uber Elevate in the Advanced Technology Center. And today we're going to talk about reproducible research with Bazel. This is the result of a little bit more than a year of work together with my colleague Romain Penec. And I'm very excited to show you what we've come up with today. So first, we'll introduce really quickly what reproducible research is about and how Bazel can help with that. Then we'll show you the capabilities that we've packed into our research platform before we go on to talk about some of the pain points we encountered along the way and how we solved them. Finally, I'll quickly talk about the future work that we're planning for the foreseeable future. So what are the challenges of reproducible research and how can we use Bazel to help? So reproducibility in research has been an historical challenge, especially in life sciences such as psychology and biology. You can imagine how hard it is to reproduce those experiments that involve human subjects. Well, it turned out that software-driven research is also hard to reproduce, and we're actually in the middle of what some people call the reproducibility crisis. So this research platform is trying to help with solving this new crisis in reproducibility that involves more and more complex software. So how can we use Bazel to help? As many of us know, Bazel is a great tool to build software. Well, it turned out it can build more than just software. It can build pretty much anything that you can represent as a directed acyclical graph. And when you look at a research pipeline, it's actually a very good example of such a directed acyclical graph. So on the right-hand side of this slide, you'll see that the research pipeline usually starts with some data. You write some research code, you use someone else's previous research, combine the resulting models. You have to depend on some configuration parameters, and in the end, depending on the research, you may end up with a simulation. And finally, you get your research results. And the end product is a research paper. So keeping that in mind, you may think that we can just tell researchers, okay, now we're going to use Bazel and everything will be reproducible. Well, it's a bit harder than that. And there is a lot to do to bridge the gap between Bazel and our researchers' audience. And that's what this research platform is about. So let me talk to you about the capabilities of Uber Elevate's research platform. So when I first started to think about it a year ago, I tried to identify the specific constraints of research engineering. And the first one that was fairly obvious is that when you write research code, you're constantly interacting with an unstable code base. You need to be able to pick an external repo and build upon it. You need to be able to accommodate some requests for new tools, new libraries on an almost daily basis. So this is a bit different from the traditional software engineering where things are usually a bit more stable. The other thing is that you are interacting with people that are not software engineers. So like researchers, interns that are writing code that will be part of your code base, but they're not software engineers. So you need to interact with them in a different way. The second point I'd like to make is that the research workflow itself is very different. So you need to be able to accommodate a lot of introspection capabilities, the ability to extract things out of the sandbox in a way that you wouldn't need with a traditional software engineering setup. Finally, when it comes to data science workflows and machine learning, you need to be providing interactive interfaces and development environments that data scientists are used to working with, such as Jupyter notebooks. And the last thing that is, in my opinion, very important is how do you actually sell this new way of working? How do you make people adopt Bazel and the Bazel graph? It's not only going to be about reproducibility. You need to add additional benefits. And one of them is the ability to scale their experiments to the cloud. And we'll talk a little bit more about it in the next couple slides. The key element to tackle this problem and address these constraints was to find the right dose of pragmatism and hermeticity. And we achieved that using Docker for the pragmatic side of things. So anytime we need to react quickly, we use Docker to track dependencies. And when we're shooting for more reproducibility and mitigating more technical debt, then we'll pick the way of hermeticity, and that's where we try to track everything using Bazel. So by using both Docker and Bazel in a smart way, that's how we can address the constraint that I just mentioned. So what are the issues of being pragmatic? It comes with slight compatibility issues when you declare dependencies in the Docker file. And that's because when you're going to package an application using Bazel, it won't be aware of those dependencies. So there is a slight risk of reduced reproducibility, but we have strategies to mitigate this. We'll talk about it a little bit later in the presentation. In terms of advantages, this setup allows us to address most of our research engineering constraints. On top of that, it adds a layer of control to make the research platform more portable across operating systems. So now let's look in the guts of the research platform. So we start with interacting with the research platform using Make. And we don't use Make to build software, but just as a convenient way of interacting with our Docker machinery. Once you've built and logged into the research environment, you can use Bazel. And here we integrated most of the useful language rules that allow you to build research software in pretty much any language. We make heavy use of the Docker rules and the Kubernetes rules as well. In orange, you can see those are some homemade rule sets that we developed to address some specific research use cases. Finally, we integrate all those rules inside of our workspace, and we already have several research projects that are working on top of this research platform. And one of the biggest advantages of this setup is that it allows our researchers to directly scale their experimentation on the Google Cloud Platform using Bazel. So how do you use the research platform? First, you need to clone it. So as soon as you've got the Git repo of the research platform cloned on your dev machine, you can start using Make Project. So Make Project will prompt you for a title for your research project, and then it will create for you all the boilerplate you need to start writing research code. So that means ready to use Git repo with all the Docker file and the boilerplate workspace to get ready. As soon as you have that, you use make run, and it will build the development image and gets you inside of a Bazel ready research container. So now you can use Bazel, Bazel build, and Bazel run to build your research software, machine learning model, and to interact with GCP. The dependencies you need to run it are fairly straightforward. You need Git, Make, and Docker, and this runs on Linux and macOS. All right, so now I'm going to talk to you a little bit about the pain points that we encountered along the way and what are the solutions that we put together to work around them. And the first use case I'd like to mention is machine learning, and how do we represent machine learning models as a Bazel graph. So as you can see here, a model that has been trained has 3 different types of dependencies. The first one is the data set. The second one is the training code, which is, in our case, usually Python code. And then you have a training configuration that you can represent as a YAML file, for example. The nice thing of representing this as a Bazel target is that you can then reuse this Bazel target as an input to a downstream research experiment. So in our case, we may want to use this trained model in an aircraft simulation to then build downstream research results. And you can easily do this using a gen rule, for example. We also have to be careful about those data sets because they may not fit on the developer machine. So that's why we developed some rules around Google Cloud Storage as well. Once you have this setup, you can go a bit further and do what we call hyperparameter tuning. For those not familiar with that term, hyperparameter tuning just means the ability to explore a very large number of config parameters for the training process. So we can represent this in the Bazel graph as a training configuration template, which is a templated YAML file, as well as a design of experiments that represent how you want to explore the parameter space. Once we have that set up, you basically generate as many Bazel target as combinations, and you inject those into our homemade DOE GKE rule that allows you to then launch all your jobs on GCP. So what does it look like in code? So on the right-hand side, you have our example YAML template file, where you find two parameters, algo and layers. In the build file, now you refer to those parameters using the DOE config param rule. So there is an algo target and a layers target. Then you bring those together inside the config target, which is basically declaring a full factorial parameter exploration for those parameters. And the last step is to use our DOE GKE rule, which is taking in an image, which is another Bazel target, which has packaged your software, GCS bucket to upload the results, and the DOE configuration that I just mentioned. You can also specify a node pool that you've set up on GKE. And this way, in less than 15 lines of code, you're ready to Bazel run thousands of experiments on the cloud with no more coding needed. So let's talk a little bit more about pragmatic versus hermetic and how do we handle the pragmatic dependencies. So as I said earlier, those dependencies are declared in a Docker file, so Bazel is not aware of them. So when we use Bazel Docker rules to package our application, those dependencies are not going to get picked up automatically. So what we use for this is a homemade rule that we developed called extended Python image, for example, for Python application, where you can specify a number of Debian packages in a simple array and create then an image that includes those Debian packages installed. And the way you use it eventually is by using your favorite Py3 image rule and using the base attribute together with the target that you define with extended Python image. So that makes it very easy to ship those dependencies even though they're not tracked by Bazel. Last but not least, let's talk about traceability. This is very important because a lot of researchers will share their research results, share them per email, send some archives around, and we want to be able to maintain this reproducibility outside of the Bazel graph. So the way we do this is by integrating the stamping step in our Bazel graph. So as you can see on this diagram, when you use the workspace status command option of Bazel build, you basically add an additional node that will be re-executed every time. And this way we're able to include, for example, the git commit hash as part of the simulation results. So what can we do to keep improving reproducibility of research software? Well, the first thing we want to do is to open source our research platform, and that will have a global impact, hopefully, and help other teams have their own Bazel-powered reproducible research environment. In our team, we're going to try to put more and more things in the build graph, use less Docker and more Bazel. So that's it. Thank you a lot for your attention. I hope you enjoyed the presentation, and we're looking forward to seeing more and more people using Bazel for reproducible research.